Okay, let's continue with the simulation of the previous video, that is a CD amplifier. So this was the CD amplifier with the values of R and okay, the MOSFET dimension was WL was taken as, of course it was considered as 50 is what we have edited, and I have labeled this as output point and this is input point, and of course I'm having a sine wave of amplitude. Okay, let me make the amplitude as around let me take it as around 100 millivolt. This is, sorry, 100 millivolt. Now before we actually do the transient response, let us first do the DC analysis. For doing DC analysis, this is the command we need to consider, that is .op. Let me do this, and if I run, it should give me the specifications what we have considered earlier. If you can see, of course this is one way of seeing the operating point. So there is another way of looking into the MOSFET specification, that is DC conditions. You can see all these things. Let me just show you what are the things that we have obtained in our calculation and what are the things that we have over here. So let me also take this. Okay, let me just show you what all these values we obtained and let us compare with the simulation values. If you carefully see these values there, okay, let me just close this and let me make it half screen, and let me see now this. Okay, see now is the value of ID is 1.41 milliampere. Can you see this is ID 1.4 milliampere? Can you see VGS is 0.967 volts or 967 millivolts? Can you see this is 967 millivolts? Where is this? This is what is 967 millivolt or 0.967 volts. And if you can see, the GM is 5.69 milli. Can you see it is 5.69 milli? And these are to just to confirm that what all designs that we have done on paper is 100% tallying with our simulation. So with these things, we have to get a gain of 0.82. And of course, let us apply a signal for first 2 millisecond. Let us take it T1 as 2 milliseconds, since I have frequency of 1 kilohertz. So for 2 cycles there is no signal. Afterwards I'm applying the signal. Let us try to see what is any phase shift in the waveform, what is the amplification, all those things. Okay, for that I have to change my modulation command from OP to transient. This is where I can do that. So this is transient. Let me see only hardly 5 cycles, because every cycle takes 1 millisecond. Let me take it as 5 millisecond. So this is starting from 0 with a time step of 1 microsecond. If I run now, I can see this is my waveforms. I should add the waveforms. Let me add traces corresponding to input and also output. Let me add them. So this is what is input and output. Let me just make sure that this is, let me make it in different panes. Of course, if you can see what is, okay, let us compare our paper design. We actually did some values now here. Can you see this is 1.288 and this is your input voltage. Input is around 0, that you can see here. So let me just have both the cursors on this. So let me take one cursor on the, this is on the input side and this is moving on output. Can you see this? The channel 1 is output, channel 2 is input. Can you see the input amplitude is 0 here? This is your input amplitude 0, which is exactly here also 0. And what is the corresponding output voltage? It is 1.287. That's what is 1.288. So can you see this? This is this is what is output here, and that is what is the channel. If you can see, this is actually channel. This is channel 1, which is moving on the output, which is moving on the output, and this is channel 2. This is channel 2, which is moving on the input. Can you see? This is just trace back here, trace back. Suppose if I move this, can you see, is it actually moving along this? So this is actually on channel, sorry, it's on input. This is my input. See here, this is channel cursor 2 input, cursor 1 is output. Now when you're not applying any signal, it is 1.288 volts, that is DC voltage, VD. And let us see what is the gain of the amplifier. So once you apply the signal, so you can see the signal is of 100 millivolt top and 100 millivolt down. That is, this is peak to peak is 200 millivolt. So in order to see that, let me just have both input and output waveforms on different pane. So let me take the output onto different pane. This is how it looks. So what I'll do is I will move the cursors on top and bottom of its waveform, which will be having a difference of 200 millivolt. So which you can see here, you can carefully observe here. Can you see this is, can you see this is, okay, what is that? Can you see this is 200 millivolt? This is 199.68. That's exactly 200 millivolt, which is this. You can see the output. So if you double click on that, the entire cursor will move on the output. Can you see now this is 163.59. Now if you find the ratio of, 163, can just slightly slant it, 163.59 divided by 200. Can you see the gain is 0.8175. This is 0.8175. This is the gain of the amplifier. If you can see there, so this is the gain of the amplifier. Now we have verified the gain, and you can see it is out of phase. So sorry, it is not out of phase, it is in phase. So you can see both are tracing simultaneously. So input is increasing, output is also increasing. Let us verify this. What is to be verified? This input maximum, we found it as 1.57. How to verify that is, you can see now I have a space. This is at 1.2, this is at 1.36. You have a lot of space till it goes to linear region, and you have a lot of space till it reaches 0. So what we'll do is, now let us increase the amplitude less than 1.57. Let me make the input amplitude as 1 volt. Let us see what happens. I'll go back here and I'll change the amplitude to 1 volt. This is now 1 volt. Let me run this. If I run, you can see now you are comfortably getting the input as well as out. Can you see the input is going from 0 to 1 and to -1. So this is 2 volt peak to peak. Can you see the output is not going to this saturation level of 2.73? It's not going. It's less than, it's close to 2.1 or 2.2 volts, and it is not touching 0, meaning it is still swinging in the available swing. Now let us make the input amplitude as 1.57. If I make the input amplitude as 1.57, the output will simply glance the 1.57. If I just run it now, you can see the bottom one is almost touches ground. It's almost touching ground here. So let me just let me make this bit bigger, and or if you want to make only see this, you can see this is almost touching. This is almost, how much is the voltage? It is 114 millivolt. It's almost 0 like. Suppose if I increase the voltage beyond this, like okay 1.6 or 1.7, if you can see there, if I make it 1.7, and if I run, you can see this is clipping. Can you see this is not a pure sinusoidal? Can you see that sinusoidal is having like this, but this is bit like clipped off. Now why it has clipped is because at the bottom it is touching this 0, it is touching this 0 here. So when you are increasing amplitude, so that's why the maximum input amplitude that can give a undistorted waveform is 1.57. We saw in the previous video how did you got it as 1.57. If you apply any voltage less than 1.57, you'll be certainly getting a perfect sine. Okay, that's it about the CD amplifier. Let us move on to the next circuit, next design, where we are seeing this circuit. So this is our next circuit. So this is the circuit what we are being given. We are asked to find what is the gain of the amplifier. Correspondingly, we are asked to find, of course, we are assuming a current of, I think, 1 milliampere flowing through this. This is 1 milliampere flowing, that is an assumption. And of course we are assuming Kp is equal to 200 microampere per volt square, and VTO, all those things is the typical values. We are asked to find gain R1, Rin, Rout. So let us start listing the equations what we know about this. So before that we have to identify what is this circuit is. So if you can see we are applying the input voltage to the source, and this is DC ground. Okay, this is like DC. Okay, I can write this as some DC voltage which is derived using VDD and R1 R2, and we have this, and I'm applying the input voltage here and I'm measuring the output voltage here. So this is also AC grounded. So since now this will also look like AC ground because this is a DC voltage which is coming here. So naturally, if you can see, I'm measuring the output voltage at drain, input voltage at gate. The terminal to which nothing is connected is gate, or gate is a terminal which is used as a common terminal to measure the output voltage and the input voltage. That's why the name CG amplifier. That's why the name CG amplifier. So in case of CG amplifier, we know that AV is given by GM into RD. GM into RD. So now what is GM? GM is equal to root of 2ID Kp W by L. So what is ID now? So ID, we know that it is half Kp W by L VGS minus VTO whole square. What is VGS? Is equal to VG minus VS, in which VG is VDD into R2 by R1 plus R2, and Vs is ID into RS. ID into RS. So what is input impedance? Input impedance happens to be, it is the resistance looking from here, which is Rin. So it is nothing but 1 over GM parallel with RS. Whereas the output impedance is nothing but the resistance seen from here, which happens to be RD parallel infinity, which is almost equal to RD, which is equal to RD. So these are the values that we have to find. So we are asked to find what is GM, AV. So let us find what is GM is. So GM, in this equation we know ID, we know Kp, we know W by L, everything we know, so that we can find what is GM is. So what is GM? Just slightly put it at bit slant angle so that it is GM is under root of 2 into 1 exponential minus 3 into 200 exponential minus 6 into 40 close equals, it's actually 4 millisiemens. So this is 4 millisiemens. So since we know this is 4 millisiemens, so naturally since RD is equal to 1K, the gain becomes 4 volt per volt. This is the gain of the amplifier. So since the gain of the amplifier is known to us, let us try to find in this equation. We know ID value, we know Kp, we know W by L. We can actually find what is VGS is. So what is VGS? I can write what is VGS is. VGS is equal to, but we need to find, let me find it as, okay, it is 1 exponential minus 3 alpha equals 100 exponential minus 6 into 40 into alpha A alpha A minus 0.4 whole square shift cal. So one of the value of VGS is 0.9. So let me find the other value. To find the other value, it is equals minus 1 equals shift cal. The other value is actually minus 0.1. So now out of this cannot be the value. So VGS is 0.9. So now VGS is 0.9, from which, okay, what is VS? VS is ID into RS. ID into RS is actually 1, this is 1 milliampere into 500 ohm. This happens to be 0.5 volt. So then what is VG is equal to VGS plus VS, which is nothing but 0.9 plus 0.5, which is 1.4 volt. So now VG is 1.4 volt, which is equal to VDD R2 by R1 plus R2. So in this, we know VDD, we know R2, we have to find R1. So what is R1? R1 is equal to, so what is R1 now? So I can just make this equal to, it's 1.4 alpha equals 3.3 into 200 exponential 3 divided by alpha A plus 200 exponential 3 close shift cal. So I'll get the value of R1 as 271.42 kilo. So now this is 271.42 kilo. This is what is R1 is. Okay, R1 is found. Then we are supposed to find what is Rin. So Rin is nothing but 1 over Gm in parallel with Rs. So what is 1 over Gm? It is 1 over Gm is actually 4 millisiemens. So this is 4 millisiemens in parallel with how much? RSC is actually 500 ohm. So what you have to do now is Rin is nothing but 500 inverse plus 4 milli whole inverse. So it is 500 inverse plus 4 exponential minus 3 equals, I don't know what that is, 166 ohm. 166.6 ohms. So this is R in. How much is R out? R out is actually 1 kilo, because that is equal to R. That is R. So we have these values of R in, R out, and so on. So let us do the simulation, and we are also asked to find what is V in max that is possible. Let us also find this. To find this V in max, let us write the possible time response that we can able to get it. This is your overall swing 0 to 3.3 volt, and how much is this we have? You are measuring the output voltage at this point. V0 is measured from VDD. So it's actually 1 volt drop. So this is you are actually, this is 3.3 volt, and you have a IDRD drop, which is nothing but 1 into 1k, 1 milli into 1k, which is 1 volt. So at 2.3 volt the output will swing. At 2.3 volt output will swing. Suppose if you don't apply any signal here, and if you start applying the signal here, what will happen? Till here, till this point T1, output is at 2.3 volts. Then when you apply this will actually increase and come like this. Correct? How much is the swing you have? You have a swing of 1 volt. And what do we have here? So we have something like this. So this is, so from the bottom, do you have this voltage first? So from the bottom, if I just, this is 0 means this is 0. This is 3.3 means this is 3.3. And this is V0 means this is V0. And how about this 500 into 1 milliampere? Can you see this is a voltage which is corresponding to 500 millivolt, correct? This is 500 millivolt. On top of that, I had to give VDS sat. So this is my, I have to maintain VDS sat. How much is VGS now? VGS, we got it as, how much is VGS? VGS is 0.9. This is 0.9 volt. So then what is VDS sat? VDS sat is equal to 0.5 volts. So this is another 0.5. So here from 0, it is 0.5 here. Another 0.5, it will be 1 volt. So how much swing we have from this 1 to 1.3? You have a swing of 1.3 volt. 1.3 volt. So what is the maximum swing that is possible? It is minimum of this positive and this negative swing, that is the below swing and above swing. So it is V naught max is minimum of 1 volt and 1.3 volt, which happens to be, so V naught max is equal to 1 volt. V naught max is equal to 1 volt. So if V naught max is 1 volt, then how much is Vi max you can think of? So we know that AV is equal to V naught by V in. I can say this as max, this also as max, there is no difference, is equal to 4. How much is V naught max possible? This is 1 volt possible, so I can find what is V in max. So V in max that you can apply so that it's not clipping on the top is given by 1 by 4, which is nothing but 250 millivolt. If you apply any amplitude less than 250 millivolt, it will be below this 3.3 level. If you apply more than 250 millivolt, so it will going to be clipping at the top. So here you have at the bottom you have up to 1.3, but it doesn't mean that if you have 1.3 you can utilize this entire swing, because if you want to utilize the entire swing at the bottom, so you have to have the equal amount of swing on the top, but you have a limited swing at the top, which is 1 volt. So the maximum swing possible is hardly 2 volt in this case. 2 volt in this case. So let us go back and try to do the simulation. So what I'll do is I will go back to this and maybe let me copy this same circuit and try to modify some of the parameters. So what I'll do is I will save as CG amplifier, because that is a CG amplifier. Let me make the necessary changes. Okay, I'll move this input voltage from here to here, and this my capacitor also move from there to here, and my output is not this point. I will move my output from here to, okay, let me just take this output from here to here, and let me insert a resistor also here. So I have to have a resistor. So this is my resistor. Let me change this. Okay, let me cut this wire. Let me cut this also. Let me cut this also. So let me make this correction. So this is where I'm going. So now we have done. So this is actually RD. The value is 1K, and this is 500 ohm. This is 500 ohm. So my input is actually here. Let me move this from this to this, and okay, let me connect this to this, and let me connect this here, and let me connect this to ground. Let me have a source resistance of how much? It is hardly 10 ohm. It is hardly 10 ohm. Oh, how much was that? Is it 500? Okay, I have taken it as 500 ohm. So maybe okay, with this as 500 ohm, let us continue. So this, okay, let me change this to first a lesser amplitude. Let me just take it as 100 millivolt. If it is 100 millivolt, as per the gain, it should be 400 millivolt is the output signal. So this is our resistance, and this value of R1 what we found is 271.42. Okay, 271.42 kilo ohms, and this is actually 200 kilo ohm. 200. Okay, this is done, and this is 1k. This is okay. W value is 40. Let me make this 40. So everything is done. I hope okay all these values are fine. So let us first do the DC analysis. So for DC analysis it is this. So I have to get these specifications. So what are the specifications we should get? I have to have a GM of 4, ID of 1 milliampere, VGS of how much? 0.9 volt, all those stuff. Okay, let us see that. Do I have all those values there listed in my... Okay, this is the thing what I have. So now, okay, these are, let me just correct it out. Let me take out, let us make this a bit clear. So this is my circuit. This output, let me connect it here. So let me connect this, otherwise it will not be visible in my list. Okay, this is input. Okay, if I run it now, since I'm doing dot op, so I will be getting the specifications. Okay, what I'll do, let me go to this view and output log. If you see the output log, can you see the current ID is equal to 1 milliampere as expected here? So we expected a current of 1 milliampere here. And then what else? The VGS is 0.9, that is 9 into 10 power minus 1, which is 0.9. And can you see GM is 4 milli? GM is 4 milli. Okay, these are the specification. Of course, you can see this VD is also the voltage at this point. Of course, VDS is now, how much is VDS? It is 0.5 dropped here, and here it is 1 volt drop. 3.3 minus 1.5 is 1.8 volt. Can you see this is 1.8 volt? This is VDS, which is 1.8, which is nothing but 3 volt. This is 3 volt minus 1 volt minus 0.5. So 3 minus 1.5 is 1.8. Sorry, 3.3 minus 1.5 is 1.8 volts. So all our DC conditions are satisfied because it is going as per our design, and it is the same as the simulation result. Let us see what is the gain. So gain happens to be 4 now. So for finding the gain, let me do the transient analysis. Okay, this is fine. It has been set in the previous case only. Now if I see the input and output waveform, of course, as you can see now, as per this input is swinging around 0. This is Vin, it's going up to 100 millivolt here, and it is at the bottom, it is minus 100 millivolt, and output will want to swing around 2.3 volt, go up and come down. So let me just okay, let me have it on a single pane. So what all things I have to add traces. One is the input. You can see this is input. Of course, now input is okay. Let me name the input over here. So you can see a shift of 500 millivolt because I'm observing the output, okay, input waveform after the capacitor. Let me go back to my circuit and change my input position. So this is not my input. Let me measure the input here. So what I'll do is I will slightly change my input observation point from, okay, let me just take out this. Okay, I will measure it here. So where I'll measure, let me connect the input here. You can see now I'm measuring the input here. Now it will not have any DC shift. It will be starting from 0 up to 100 millivolt. Now you can see now. See now, is it starting from 0 now? Actually earlier I measured at after that capacitor, which will have a DC voltage of 500 millivolt, which is ID into RS. So I was actually measuring here the input voltage earlier, so that's why it has DC shifted by 500 millivolt. Now I'm measuring here, which doesn't have any DC shift. So this is my input. So let me also measure the output. So to measure the output, you can see it will be around 2 point. How much is the voltage? It will be centered around 2.3 volts. So let me see now. Can you see it's around? So this is centered around 2 point. Okay, this is centered around 2.3 volt. Can you see here? If I just move this, okay, let me move it on the output. See, is it not 2.3? 2.299. So this is my uh, output when the input is not applied. When the input is not applied, let me put it on different pins. So let me put the output here. So this is what the signal is. Let me see what is my output is. So input peak to peak is 100 millivolt. Output peak to peak should be 400 millivolt. Sorry, peak to peak is 200. Then output should be 800 millivolt peak to peak, because it is 200 into 4 times. So let me just see that. Can you see this is almost there? So how much is now? Let me before, okay, now we will do one thing. So let us now measure the output to input voltage at this point and try to find out how much is the gain there. So what I'll do now is I'll show you what is that I'm trying to show. So let me have the input measured here. Let me have the input measured here. So this is my input measurement. Let me bring this red one here. This is red one. Now let me take out this totally. I'll take out this totally, delete this cursor. Okay, I'm having only this. Okay, this is my this is the actual input voltage that is reaching the amplifier. So this multiplied by 4 times I'll get the output. This multiplied by 4, because this is the actual input. So even though, if you can see here, even though I have an amplitude of whatever the signal, but how much is reaching over here matters. So this signal is amplified by 4 times. So that's what I'm trying to see now. See now, this is my input amplitude. How much is the input amplitude here? The input amplitude, sorry. Okay, what I'll do, okay, let me do this again. So let me have one cursor here at the top, the other cursor at the bottom. How much is peak to peak? Peak to peak is how much? 20 millivolt. So 20 millivolt is the peak to peak. How much should be the output? Output peak to peak, V naught peak to peak should be 80 millivolt. So should be 80 millivolt. So let me just click on this and try to find out how much is that. Of course, when it is 20.8 means 20.8 into 4 is close to 81, 82 something. If you see now, can you see it is 83.4? So how much we had? It's actually 20.9. Let me see. Can you see it is 20.81? It is 20.81 millivolt. It is now 20.81. Sorry, 20.81 into 4 times is 23.24. So this is actually 23.24. So this is what is the amplification. Both are in the same shape. Both are, if the input is increasing, output is also increasing. That means That means here the gain is GM into RD, GM into RD. Now the gain is actually 4 from here to here. From, okay, if you consider this as input voltage and how much is the output voltage you're getting, it's actually GM into RD times so and so. But how much is the signal you applied here? You have actually applied here 100 millivolt. Let me show you what is happening here. Suppose if I see, now let me compare this input voltage, which is the signal voltage, and the input that is reaching this. So what I'll do is, let me not take the output now. Okay, let me use one more pane. Let me just put it below. Let me apply what is the input. See, this is my input. My input is 100 millivolt. By the time it reaches here, there's a slight phase shift, and as well as the peak to peak has reduced from, this is actually 200 millivolt peak to peak, it has reduced to 100 millivolt peak to peak. Let me show you what's happening. At this point it is 200 millivolt peak to peak. So this 100 is peak to peak is 200 millivolt. That's what is this. By the time it reaches here, the amplitude has reduced to 20 millivolt peak to peak. Because if you can see this, how much is this peak to peak? That's what we measured in the previous calculation. Can you see this is 20.6? So now, why this much of huge reduction is happening over here? It's because, let me show you why it is so. Let me just show that. Okay, we need to quantify why that this 200 millivolt peak to peak has reduced to 20.6 millivolt peak to peak. Let me just satisfy you people with the theoretical explanation for this reduction of input amplitude from, okay, what we have here, okay, let me rewrite only that portion. What is the portion we are talking about is, we had input of 100 millivolt peak or 200 millivolt peak to peak. It is now having a RS of, or a R signal of 10 ohm, and it is connected to a 500 ohm RS, and this is your transistor whose, okay, emitter is, whose source is connected. We know that when a source is connected, the resistance is 1 over gm. So don't you have a resistance of 1 over gm in parallel with RS is across this? This is 1 over gm. So we know that 1 over gm in parallel with 500 in the previous calculation, because we found that RS is, how much was that RS? It was actually 166. So this is actually, this entire thing is 166.6 ohm. This is 160.66 ohms. This is what is this. So what you can think of now doing is, so you have a 100 ohm, sorry, you have a 10 ohm R signal, and you have a 166.6 ohm overall Rin. So now how much is the Vin that you are getting if this is Vs? So shall I say V in is equal to Vs multiplied by R in divided by R in plus R signal, which is now equal to Vs multiplied by, how much is R in here? So R in is 166.6 divided by 166.6 plus 10. So how much is it? Is that 10 what we have connected in our case? Okay, this is 10. This is series resistance 10. So now let us go back and try to calculate. So is it now, suppose now this is 100 milliwatt, it is 100 into 166.6, sorry, 6 divided by 166.6 plus 10. Okay, how much is this we are getting? We are getting it as, this is coming out to be 90. 94.33 millivolt. Why there is a mismatch in the values? Okay, let me just go back here and try to find it. Okay, this is okay. I'm getting what is this problem is. This is due to this capacitor what we're taking. So let me just do one thing. Okay, this is the voltage that you are supposed to get. Let me change that frequency. Okay, I'll tell you. Instead of having it at 1 kilohertz, let me have it at 100, okay, maybe 10 kilohertz, maybe 50 kilohertz, maybe 50 kilohertz. If I make it at 50 kilohertz, you can see this beauty thing. So when I make it 50 kilohertz, let me change this time also to, so if I want to see 5 cycles, 50 exponential 3 inverse. Okay, engineering 20 microsecond. 20 means, let us make it 5 cycles means 100. Okay, 1 millisecond. Sorry, 100 microsecond means 1.1 millisecond. 0.1 millisecond. Now you can see the magic. Okay, is this changed? This is changed too. This is now, let me run it again. Let me change this time period. Okay, this, okay, let me make it, this is my 10 kilohertz frequency, sorry, 50 kilohertz frequency. Let me change the time to, if I make it, what's happening here? So I have a frequency of, this is a frequency of 50 kilohertz. So I have, oh, it's a high pass filter. It's a high pass filter of, one second. Okay, wait. When it is this should be changed to, okay, now you can see this will be close to that. Okay, this is frequency of, because when you have a capacitor here, this is now acting like a, this is acting like a high pass filter. So when you have a high pass filter, okay, I have to go for a higher frequency. Let me just, okay, one second. This cannot be 10. This has to be, let me make it 10k and let me run this. Okay, now you'll get it. Let me stop it and then zoom some portion. Let me zoom this. Let me zoom this further. Now let me show you how much was the input peak to peak. Input peak to peak is 100 or 200 millivolt. That's what we have here. This is, this is what is almost close to 200 millivolt. 200 millivolt. Let me further zoom this. Let me just keep it. This is, I'm here. So I'm here. So let me find how much is this peak to peak. Can you see it is 97 millivolt? This is what is 97 millivolt, and output is having a peak to peak of, oh wait, this is not the peak to peak. Let me keep the peak to peak of this. So this is the actual input that is applied to the amplifier, which is 139. It is 139 millivolt is V in peak to peak, and the output peak to peak is 500 millivolt, 557 millivolt, 557 millivolt. So let us see these equations that what we have now. So now what is this 94.33 into 2? You're supposed to get 180. You're supposed to get 183, 188 millivolt, which is twice of this. 188 millivolt, but you're getting 140. That is fine. If you see this gain, if you see the gain of this and this, so this has got a gain of, so this is the input voltage you applied and this is the output voltage you got it. Is it now 139 divided by 557, which is close to 4, meaning this is the input voltage that you applied, this is the input voltage that you applied here. So now out of 100 millivolt peak or 200 millivolt peak to peak, you are getting close to 139 millivolt as the signal that is available to the amplifier. This is amplified by 4 times and you are getting the output peak to peak of 557 millivolt. The purpose of having this is actually to have the DC current flowing through this, and it's not the entire 100 millivolt reaching here. Out of 200 millivolt peak to peak, you are hardly getting 139 millivolt peak to peak because of this R in, which is nothing but this in parallel with this, and you have a R signal also associated with this. So this is how you can able to understand the CG amplifier, which is the practical case. This is your VS, something is reaching here, out of this how much is reaching the output signal. Okay then.